All right, so the next lesson, 814, is called What If It Does Not Grow? So instead of talking about things increasing, we're talking about things that are decreasing. So the first part of this is talking about, decreasing or a decay, exponential decay instead of exponential growth. So we're also going to be talking about different types of multipliers. So we've got a little bit of that, and then we are also going to talk today about negative exponents again, which ties in a little bit. It says the penny lab. What about situations that do not increase? In this activity, you will explore a situation that behaves exponentially but decreases instead of increases. This is called exponential decay. So what you can do independently, if you're curious, because it is kind of fun, especially if you have a younger sibling and they want to see you do something like this, you'd want to start with 100 pennies, and you want to dump all 100 pennies onto a single surface, floor, table, whatever. And when you dump them, you want to remove any of the pennies that are tails up. So the only pennies remaining are going to be the ones that are heads up, and you're going to count them. So we will assume that after 0 trials, we have all 100 pennies to start, okay? After we dump the pennies out, we've performed 1 trial, we're going to count the pennies and say that there are still 59 heads up. Now, I actually did this trial myself. That's where these numbers are coming from. So then what you're going to do is you're going to pick up all of those 59 heads up pennies, or how many ever you have, shake them and dump them onto the table again. Remove any pennies that are tails. And the second time I had 27 that were still heads up. And then you're going to take those 27 heads up penny, put them back in the cup, dump them out. And the third trial, I had 11 that were still heads up. You're going to continue doing this until you don't have any heads up pennies left. So after the 4th trial, I still had 9 heads up. After the 5th trial, I still had 7 heads up. And after the 6th trial, I still had 4 heads up. I actually stopped at that point because I ran out of table. Is it possible that a team conducting this experiment might never remove their last penny? Is it possible? Sure. Hypothetically, it's possible, but only possible if they kept getting heads. If they kept landing heads up. And that's it. It would just have to keep flip heads up, flip heads up, flip heads up. And we know statistically that's not going to happen for very long. Would the results of this experiment have been significantly different if you had removed the heads pennies instead of removing the tails? And we would say no, it should not be statistically very different, because a fair coin is equally likely to land heads or tails. And we are assuming that we are using a fair coin. If you started with 200 pennies, how would this have affected the results? So think about it. What would have happened on the trial before I had 100? Hypothetically, if I started with 200 pennies, I would have gotten somewhere near 100 after the first dump. So this might have hypothetically taken me only 1 extra trial. So probably only 1 extra trial, because we remove about half each time. So if you had gone from 200 to 100, that would have been your 1 extra trial. Graph your data carefully on the lesson 814 resource page. Stack your team's transparency. So what we were going to do was we were each going to graph like this, right? And so we were each going to have a graph like this, and then we were going to stack them on top of each other so that you could see the curve of all 4 of them. And the curve of the 4 is a very similar shape. And I don't know if you can see this one well, but this is the one that I had from a previous year. And you can see that you started at slightly different levels here, but that they all kind of had the same general curve pattern, getting closer and closer to the x-axis. And eventually, because this is a real experiment with real pennies, we would have really eventually ended up touching the x-axis. It would not have been an asymptote in real life, even though if we are to model this, we will model it with an equation that would have an asymptote. Stack your team's transparencies. We did that. Where does the graph cross the y-axis? It should cross the y-axis at 0, because when we had Sorry, 100 because you're at 0 X's, 0 trials, 100 pennies to start. Does it have any asymptotes? We would say yes, that the graph does, and it would be y equals 1. It would be the x-axis. Your graph would be discrete because we count pennies. It is not continuous. We don't measure the number of pennies. Remember that I did just say, though, even though the graph has an asymptote of y equals 0, the real life situation would eventually have 0 pennies. Heads up. Is the data in this situation increasing or decreasing? Decreasing. We're losing pennies. What does this mean about the multiplier? The multiplier would have to be less than 1. It would have to be some sort of decimal between 0 and 1. Using what you know about the probability of flipping a fair coin, what would you expect or estimate the multiplier to be? Well, we said to get from 200 to 100 would take about 1 trial because we're losing about half of our coins each time. Write an equation for an exponential function that models the data. Make sure you also write a let statement. So our first let statement would be let x equal the number of trials and let y equal, or I guess it doesn't really matter. Let y equal number of heads up pennies, I guess. So let's see, let's go with y equals, initial value was 100, multiplier is 1/2, and x would be the number of trials that we've performed. Now, because it's discrete, we would be better off with a sequence notation, which would be t of n equals 100 times 1/2 to the n. If we're going to do that, then number of trials would be n, and the number of heads remaining would be t of n. What output does your function give for x equals 0? So if I were to plug 0 in, anything to the 0 power is 1. 1 times 100. We would start with 100 pennies after 0 trials. So no trials have taken place. So we have all 100 pennies. And you guys can see why this is probably not a group activity we would be doing in class currently. If we look at the back side, we're going to continue, same concept, same scenario. E, could there be an output value for x equals -1? So if we went 1 trial earlier, that would be 200. We'd have to double to get 1 trial earlier. And that would be if we started with 200 pennies. In the context of the situation, what should the domain of the model that you wrote in part C be? The domain would have to be integers. That would include the positive, the negatives, and the zeros. Write the appropriate domain. With the appropriate domain, what would the graph of your model look like? It would be discrete. We can't do 1.5 trials. We also can't have 1.5 heads up. The graph in part F looks like what graphs you saw in 813. It is curved, so it is geometric. What are the first few values of this function? So after 1 trial, we have about 50, right? I actually had 57 in the real, trial where I was actually dumping pennies out. But according to our model, then we would say 50, then 25, then 12.5, then 6.25, and so on. And our equation would be t of n equals 100 times 1/2 to the n. Notice, though, it's not going to work in the real world. It's a model. It's going to be close, but it's not going to be 12.5 heads up. It's not going to be 6.25 heads up. All right, another thing that comes into play in geometric decay is half-life. I went just a little too far there. Carbon-14 dating is used to approximate the age of ancient discoveries and to learn more about things like dinosaur fossils. Scientists have studied the rate of decay of carbon-14 and have learned that no matter how much of this element they start with, only half of it will remain after 5,730 years, which is called its half-life. All living things on this planet contain the same proportion of carbon-14 relative to the amount of overall carbon-14 in their bodies. Knowing how much carbon-14 to expect, scientists can measure how much carbon-14 is left in ancient items to figure out how much time has passed since the object was living. So this is how we date a lot of things, including things that are not ancient. If a living object contained 100 grams, their half-life would be 50 grams. Now, it's going to take 5,730 years to get from 100 grams to 50 grams, but that's what they would have left as their half-life amount. After 2 half-lives, we would be down to 25 grams, which would be half of the 50. Draw a graph showing the expected amount of carbon-14 in grams remaining after X half-lives. Now, what you'll notice is that this is the same pattern. We would start with all 100 of our grams, and then we would have only 50 after 1 year. We would have 25 after 2 years, and we would sort of do this decreasing pattern. Now, you might be saying, whoa, why are you connecting that? Well, there is a value of carbon-14 in between 0 and 1 half-life. If all 5,730 years have not passed, you can still figure out how much carbon-14 is in it and how long it's been since it died. And that would be how we would be testing things that have been dead for, say, 2 or 3 years versus something that's been 5,000 or 11,000 years. Draw a graph showing the expected amount. We've got that, and it is curved because it is continuous. So this is your y equals 100 times 1/2 to the x. So if you compare, we've got our sequence notation up here for the pennies because we can't have half a trial and we can't have half a penny. But down here, the continuous function is appropriate because we can have less than 5,730 years pass. We can have between 100 and 50 grams. All right, 857. In addition to helping you learn about exponential decay, half-life can also provide insight into the meaning of exponents that are negative or 0. Using your function from the previous problem, what output does your function give you for x equals 0? So we know that if 0 amount of time has passed, it still has all 100 grams of its carbon-14. Does this make sense? Well, it makes sense because no time has passed, so there's been no decay. So that seems reasonable. According to your graph, how much carbon-14 should there be when x equals -1? Use this information to make sense of the value of 1/2 to the -1. So if we did y equals 100 times 1/2 to the -1st, we would get a response of 200. The same as we did for the pennies. If we went 1 trial earlier, it would have needed 200 pennies to start. Or in this case, 200 grams, because we're talking about the amount of carbon-14. Now calculate the output of your function when x equals -2. Use this information to make sense of the value of y of 1/2 to the -2. So what do we know already about negative exponents? We know that negative exponents means that something is sort of in the wrong location. So if we did, for example, 1/2 to the second, we know that that's 1/4. But 1/2 to the -2nd means that these are in the wrong location, and it should be 4/1 or just 4 as if it were in the numerator. So if we want to start talking about variables, if we had x to the -2nd, that's the same as 1/x to the second. If we had 3 to the -2nd, that's the same as, well, 3 to the second would be 9, so 3 to the -2nd would be 1/9. Likewise, the one they have on here is 2/3 to the -2nd. Well, if I did 2 to the second, that would be 4, and 3 to the second would be 9. But since it's a -2nd, they're in the wrong place, and it would be 9/4, the wrong part of the fraction. What is the effect of a negative exponent? It makes the answer the reciprocal of the base. It brings it back to having a positive exponent, or brings it back like a positive exponent if you take the reciprocal of the base. So for example, 1/2 to the -2nd is the same as 2/1 to the positive second. Last but not least, just a few for us to practice at the bottom. So 1/5 to the -1st. Well, 1/5 to the first would be 1/5, but then if we took the reciprocal, 5/1 or just 5. 5/8 to the first would be 5/8, but since it's to the -1st, we need the reciprocal, 8/5. 1/3, well, 1/3 to the second would be 1/3 times 1/3, which is 1/9, but the reciprocal would be 9/1. 2/3 to the negative third. So what I suggest when you start getting to anything just a little bit more complicated would be to actually write out, what would 2/3 to the third be, right? You would do 2 to the third over 3 to the third, and you would get 8/27. So this one would be the reciprocal, 27/8. So you can always take that extra step yourself if you need it. And also, if you've got something to the negative first, it means that your numerator and denominator are in the wrong spots, or they need to be flipped for a reciprocal. So b moves up to the numerator, a to the second moves to the denominator, but nothing else changes because your exponent was -1. Last but not least, if I want to take this one step at a time, I can do x to the third. Y to the second to the third is y to the sixth. Z to the third is z to the third. But this one that had the negative exponent would be if I used the reciprocal and had y to the sixth, z to the third in the numerator, and the x to the third in the denominator. So it's all about remembering when your exponent is negative, it is about location, 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 just like real estate.